And we're live. Hugo Bown-Anderson here from Coiled with Kirill from Geoscience Australia. Kirill Kouzoubov, a senior software engineer at Geoscience Australia. We're here today to talk about imaging entire continents with Dask, in particular, talking about the work Kirill and his team does at Geoscience Australia on large-scale temporal processing of geospatial data. Oh, got a bit of feedback there. Geospatial data using Dask. Good morning, Kirill. Great to see you.
Good morning. Great to see you too, Hugo.
And I can truly say good morning to you. I usually say good evening on these because it's morning for me, but it's usually evening for my guests. But I can truly say good morning to you because you're in Australia as well.
Absolutely. It is indeed morning here in Canberra.
Yeah.
Pretty lovely so far.
In our nation's capital.
Exactly.
Probably little known fact for a lot of people tuning in from the US as well. I think a lot of people tend to think Sydney it's kind of, Canberra's like the DC of Australia in a lot of ways. Right? I can truly say good morning to you. I usually say good evening on these because it's morning for me, but it's usually, and I'm turning that off. All right. I had the YouTube stream to make sure it was going successfully in another browser. But having said all that, I'd like to welcome everyone who's watching and tuning in to listen and chat about these, analyzing these patterns for large scale temporal processing of geospatial data and Sentinel-2 data in particular. If you could introduce yourself in the chat, that would be fantastic. Let us know who you are, what you're up to, what your interest in Dask or geospatial or Sentinel-2 is. That'd be awesome. And while we're waiting for a few more people to turn up, I thought, Kirill, you could just tell us a bit about your background and how you got involved in data and software engineering and all of these types of things in Geoscience Australia.
Thank you. Yeah. So I've been in Geoscience Australia for about 4 years now, and primarily working on the Open Data Cube system, which is Earth observation data sort of exploitation system. We maintain a large collection of various satellite imagery and derived products, and develop a software that allows data scientists to use those products and the data and to generate new data in Python using we use Dask quite a lot for both batch processing large amounts of data and also in the notebook, so that the data experiment sort of turnaround is quicker. But when essentially we're using Dask to parallelize data for satellite imagery data.
And we're going to see a lot of that in action. I'm also interested in how, of course, I'm interested in like adoption of Dask. I feel like there are a lot of people who probably would be well served by using Dask who aren't currently. So I'm wondering how you kind of found Dask, or how Geoscience Australia found Dask, and maybe how you found Python originally, or just kind of the trajectory into PyData.
Yeah, so when I joined Geoscience Australia to work on this project, this was already done in Python, which is an obvious choice for data scientist type of thing. Andrew Hicks, a colleague of mine, was very much into Dask, and we were using it initially, maybe not quite the right way, but we were using it as just as a kind of remote execution backend. We haven't really embraced the arrays and stuff properly at the time, but we learned, and now we generating X-array based Dask-based X-arrays from geospatial data, and leveraging all the sort of rich ecosystem developed in the Python space for this. So my first experience with Dask was working on the project, on this Open Data Cube project. My first experience with Python was back in, 2000, using Matplotlib and NumPy as a replacement for MATLAB, and sort of experimenting with prototyping algorithms that I would later code up in C++ in Python. So
we've got a few people just tuning in from the chat. Sammy is calling in from Canada, says hi. We have Jacques from MacBox, someone from LA, someone from Prague, someone from Vancouver. Now, Amrita Gupta from the US who's a data engineer at Conservation Science Partners, interested in learning how to work with remote sensing imagery at scale. We also have Matthew Rockland, who's joined, and Matthew has written Dask as a remote execution backend. Sounds like a fine way to use Dask. And then he put a smiley face.
As in, like we were. It's like a function callback on a remote server, not as a here is an array that is partitioned and properly done.
Right. That makes sense. Well, it's definitely a first step. We have someone dialing in from Austria as well. Something you've hinted at is that there's a worldwide community of people working on this type of stuff, using Xarray and Dask and that type of stuff. And I'm just wondering how much of your work, or how much of how you think about, or the software you use, is related to the community. Is the community something that's important?
Yeah, absolutely. So Pangea is big in this space, and it seems that we are converging on using Xarray for raster data analysis. There is still some place for improvement in terms of standardizing the georegistration information and things like that. Like a more standard way of describing how pixels relate to ground locations would be nice. We have obviously one such implementation, but it would be great if we as a community decided on a standard way to represent projection information essentially on the Xarray data. But yeah, it's absolutely a global open source phenomena, and we're leveraging a lot of technologies to provide what I think is a valuable data analysis platform for data scientists.
Yeah, fantastic. So before we jump into your actual work, I would love to hear a bit about what you like about Dask, and maybe what frustrates you about Dask as well.
Sure. I mean, it's easy to fall in love with Dask. It can be very magical, and speeds things up almost like without little change to code. But as you start working with really large data sets, or need to perform batch processing at scale, things sometimes can break. Usually it's about memory. Usually the scheduler might make decisions that you don't necessarily think are right, and will sort of use up more memory than is necessary. We have come up with some ways to work around this, and as we learn, we try to understand, which way, how do you force the scheduler to operate the way is the most efficient way to deal with this data. So a lot of our processing is extremely parallel, and so there is no need to optimize for concurrency. What we want to optimize is for memory use instead. And sometimes it just works with your things like .sum and .average. It's pretty good to figure out how to evaluate the graph in a way that does not use all the RAM. But for more complex workflows, particularly when you need to assemble a lot of memory, a lot of bits in memory, it can be challenging. So yeah, so my frustrations would be with sometimes memory is hard, and sometimes I just wish I could tell the scheduler to do things in a certain way, and I'm not yet I don't know how, but maybe that will change, or maybe I will learn.
For sure. So what I'm hearing is that Dask is great when it is, but sometimes when you need to do slightly more sophisticated work, there are frustrations. And I mean, you made a statement, memory is hard with Dask, but memory is hard.
It's hard
well,
in general,
right?
yes.
So
big data.
Yeah, that's right. But so what I'm hearing is that if there were ways to communicate more intelligently with the scheduler for these more sophisticated tasks, that would be useful.
Yeah, like in our case, if we could easily say, process this temporal slice from here to there. We usually have like a fairly deep pipeline of data transformations, and they all require temporary storage. But if we can force the scheduler to say, for this time slice, do the whole lot, and because a lot of the temporary memory then disappears. So guiding the scheduler order. And I know that now with Dask annotate, we can probably start doing that. I just didn't have time to experiment with it.
And as we'll see, you've, I think, developed some pretty clever workarounds to deal with these types of problems as well.
Yeah, and I guess another thing is sometimes I want to save data and to disk as a large image, and sort of for that I need to force the computation to happen on a single worker, and that also been a little bit challenging. It's easy to it's just hard to implement in a library. I guess let's put it that way.
Yeah, exactly. So let's jump in just to let everyone know what we're going to do. Kirill is going to show us a few slides about the work they do. I want to ask about Geoscience Australia, but I think I recall that this will be in your slides, and then we're going to jump in to some notebooks and look at the work Kirill and his team does and how they use Dask.
Yep. So I'm sharing screen now. Is that working now?
It is.
Excellent. So, sorry?
So I was just saying fantastic. I was being just generally positive at this slightly early hour.
Yeah, so I gave a talk on Dask Down Under about temporal processing of geospatial data using Dask.
Oh yeah, sorry, just let me cut you off and say one thing about that. We recently had a sub-conference called Dask Down Under of the Dask Distributed Summit. And I urge you to check out all the videos that are online and to let us know what you think as well. Kirill's presentation was fabulous. There are a lot of interesting, there's a lot of interesting work done there. So check it out. Sorry about that.
Yep, cool. So I'm kind of reusing some of the slides from that talk. That's all I wanted to say. So I'm Kirill Kouzoubov. I work at Geoscience Australia as a software engineer on developing Open Data Cube software. And in this presentation, I'm gonna give a brief demo of using Open Data Cube on Coiled infrastructure, working with Sentinel-2 imagery data. Oops. So just to give you sort of our hardest task that we achieved using Dask is computing a Continental mosaic of Sentinel-2 imagery. This image on the right is a combination of how many does it say? 5.5 million input TIFF files or something like that have been all processed together to form this clear. It's not quite clear. There is still some clouds shining through, but and nevertheless, it's much cleaner data than the inputs. This is just like to give an idea of how the scale of data involved that we managed to process and using Dask. So the way we done that is we partitioned the space into this 5,000, almost 4,500 squares. And for each square, we loaded the pixels across the entire year worth of Sentinel data, removed clouds, and then combined those observations to find the most representative pixel using a geometric median algorithm, which is really just a generalization of a median to multiple dimensions. So all the bands, the 10 bands I think that we use of the Sentinel-2 sensor combining together to form a most representative view of it. You can think of it the most representative color, but really there are more bands than RGB.
That makes sense. And I mean, already we're having a pretty, before doing like hardcore analysis, we're having a pretty serious data pipeline, right? There's a lot happening already.
Is a lot happening, yes. All of it is orchestrated by Dask. We are not using one giant Dask cluster here, but instead we're running we're using pretty big nodes, 512 gigabytes worth of RAM on each, and each one runs a local Dask cluster. And so we use Dask for this particular workflow. We use Dask as a distributed Dask scheduler, but on a local node only. That has a number of advantages. When you're computing it at scale, I don't think I don't think Dask will scale to a full continent processing just yet. It doesn't need to for this case because it's so data parallel. But also, this means that if a particular scheduler decides to not work or whatever, it's fine because the infrastructure will restart stuff. We're using Kubernetes under the hood and Kubernetes jobs to trigger all of that processing. And if a particular cell fails to compute, it will be recomputed. So that's how we use this. This is just a demonstration of how much data there is on the.
And can I just ask, when you joined, you weren't using Dask yet, so there were other ways to deal with this type of workflow and this amount of data?
Yeah, so previously we were using, majority of our processing was happening on NCI, National Compute Infrastructure, which is a high performance compute center. And we were using PBS jobs, and we were simply partitioning the space into smaller chunks that would fit into memory of a single thread, really, and just use a single thread processing, but concurrently across a lot of nodes on the cluster. And that's fine, except for when you're performing things like GMedian, where memory requirement is really high. And so if you have 16 cores on a machine and you're running 16 processes, each process gets 1/16 of all the memory. And so moving to Dask, moving our pipeline in IO pipeline into Dask meant that we could parallelize within the cell more, right? So within one of those squares, and that meant that there is more memory available to the process as a whole, and that really helped us for memory-hungry computations like this one was.
And did that then reduce just overall time to completion of project, or?
Yeah, absolutely. It certainly helps. Dask helps us in two ways. One, for orchestrating the batch processing, of course, but batch processing is like the final step, right? It's like pressing a compile on a finished program. And a lot of data science happens in the notebook, and Dask helps there a lot as well, because speed is one, right? So make in decreasing the time per iteration of the data experiment, but also lazy computation helps too. A lot of the geospatial processing is about sort of temporal reductions, and not all of them are hard like median. Some of them can be done incrementally. So a lot of it is some kind of band math followed by some kind of sum, and Dask is really good at that.
Great.
That quick.
That's fantastic. Okay, thanks for bearing with all my questions, but let's keep going.
Yeah, this is just the references for the algorithm that was used. I'm not going to concentrate on that much. It really just about finding the most representative pixel color effectively. It's pretty cool. Very useful, apparently, for various data processing pipelines later on. Having a clear image, having a good understanding of how this pixel looks is really useful. But so within Geoscience Australia, I work with this in Digital Earth Australia program, I guess, and we don't just maintain the software and develop the software that is the Open Data Cube. There is also a vast amount of really high quality notebooks that showcase the various data products that Digital Australia produces, but also how to work with that data in Python. So I strongly recommend people to check those out. I won't be showing them today, but do have a look. It's really good.
That's great, and I'm just posting them in the YouTube chat as well.
Yeah. Yes, please. Thanks. Today, however, we will be working with data that is not Digital Earth Australia data, but rather Sentinel-2 on Amazon, on S3 bucket. So here's a link and a picture of a website. So essentially, Sentinel-2 is a European agency satellite. It has 10-meter resolution bands for red, green, blue, and some lower resolution for infrared and stuff. Heaps of data, really good. It is, however, using JPEG 2000 natively, but that format is a little bit hard to work with sometimes. So there is this bucket that I recommend using, which basically contains the COG, which is cloud optimized GeoTIFF, view of the same data that is available in JPEG 2000, and there is a STAC metadata present in this bucket as well. And STAC is a spatial temporal asset catalog, and it's an emerging standard for describing geospatial rasters in particular. So check it out if you haven't heard of it. It's really good. And is this demo time? I think, yeah. So what I have done, I have created, I have logged into Coiled.io, and I have created an environment that contains the data cube.
And what I'll just let people know, if we have some newbies here with respect to Coiled, essentially Dask is for a toolbox for distributed compute, particularly in data science and machine learning, but works for a lot of Python code. It isn't always straightforward to get it up and running on the cloud. There's a lot of Dockerization and containerization, Kubernetes stuff that you need to get running, and then DevOpsy stuff. So what we do at Coiled is we have one-click hosted deployments, among other things, that allow you to get your Dask clusters spun up immediately. So that's precisely what Kirill's doing here. We have all types of software management tools and telemetry and that type of stuff. That's by the by, but we'll see some of that in what Kirill's doing now.
Yeah, so I have, so Open Data Cube requires a database to operate. So I made a database of Sentinel data that covers the Australia and also 1 month globally, just for examples. And this just shows how I put it into this. I'm running the database locally, essentially, but in the real deployment, you'll probably connect to something external. So this is just a script that shows how we just unzip it, and it ran really quickly, but I prepared ahead of time. I have also prepared and launched Coiled cluster with the software that I have, and it's running here. I assume, I hope. And if not, we'll have to restart it. It's okay. Things might shut down, I guess. No, it's not running currently. That's okay. We'll start it. So we are launching a cluster now that has the same environment as this notebook is running. While that's happening, we can have a look at the data that we have on the Sentinel. So we're going to import some things. There's a lot of different tools. It is still starting up. That's okay. We might have to wait because this is blocking.
yeah, that's great. But you can, if you want to talk us through some of the code that's coming up or something, or
yeah, I think one of the things I can, I guess, have a look is like this special temporal asset catalog. I think is an important thing that people should sort of hear about if they're interested in accessing data in the cloud. It's essentially a JSON format. It's a GeoJSON, but it contains all this information as to how to, where the data is and how it looks like and all of that. And it becomes a standard, and hopefully we will be able to use it. We'll be able to use collections that are managed by one entity, and everybody can load data from it. So STAC, check it out.
Awesome.
All right. So what I'm gonna go through, well, okay, so what we have is this oops, special temporal, no, hold on. We imported some code. So basically what DataCube is it's a system for, it has two parts. One is a database that manages the metadata, and the other one is the data loading part. And once data is loaded, we rely on usual sort of X-array ecosystem of tools that allow us, very rich processing environment for working with raster data. And is it done? Still doing. So what I'll show a little bit more. Let's talk about a little bit more about Sentinel-2 data in general. So Sentinel, can I zoom out somehow? No, I guess not. Partitions the world into this grid of it captures data, and then it partitions into this grid, and its individual images are about 10,000 by 10,000 pixels large, and it's kind of difficult to work with because you need to stitch them together, you need to bring them to the common projection. As you can see, as you sort of it has the partitions. It partitions world into 60 rows, and then it partitions rows into columns, and then partitions rows and columns into rows, and it has this convoluted naming convention. But with a tool like OpenDataCube, you don't need to worry about any of that, right? Once somebody figured out how to index this data into the DataCube, after that you access it based on just give me this plane of pixels at that given time. And so you don't need to worry about those things, but you do need to worry about those things if you want to work with data directly and accessing those things and accessing files. So, so that part.
And that work was done at Geoscience Australia?
Correct. Yeah. So the project started before I joined OpenDataCube, but it essentially it's a metadata management system for satellite imagery. It started off for Landsat, but we're using Sentinel and others as well now. All right. I think this thing started. Yeah. So now we have a client. We're gonna. I found some weird bugs with imports, so we're gonna have to do some workarounds to make it work.
Okay.
I'm gonna configure the cluster to access S3 buckets without authentication. That bucket is public, right? Okay. So we have our client connected that we can observe what's happening there. It's all running. Good. Move it over here. That's an old one. All right. Still, we're gonna do some stuff, and then this is what I was waiting to generate. Is like this is how Sentinel-2 passes work, right? So on this day, 5th of July. Sentinel-2 flew across Australia in three different places. The revisit time on Sentinel is 5 days. So if you concentrate on, say, Perth, it's like in the middle of this path, you'll see that there are 4 days without observations. 1, 2, 3, 4, and on the 5th day, it should come back and observe the same spot again. So this is a high frequency, relatively speaking, revisit time. So it's a lot of data. It's a lot of interesting information there. So I have...
And we just have a question from the chat. Constantine is asking, what are the double lines on the grid? Are they overlapping regions?
Yeah, so I pressed show like to see what happens globally, and I'm gonna zoom in and have a look and answer that question. So the double lines here is when the Sentinel changes from one projection, from one UTM project zone to another, right?
Okay,
So
that makes sense.
So yes, there is overlap in pixels, like particularly like in this region, you can see that there's quite a bit going on in terms of changing the projection that is used to capture the data. So it's using UTM, and as it moves east to west, it picks a different zone. So DataCube handles that for you, gives you all those data sets that you can inspect, but you can also load the data in, right? So I have, like, if I did through here, you'll see like a selection thing, but I decided not to do it live. So what we need to tell DataCube is that we want this product loaded, covering that area of the world, and for month of March, I think, this year. And we are interested in the following bands: red, green, blue, and SCL is a scene classification layer. And we want the data to be returned in this is a native projection for this region. But the resolution we're currently using is 8 times 80 megapixels instead of 10, just so that it's quicker. And it's really hard to plot imagery. It's not even Dask problem, it's like a visualization problem. When the images are large, things are hard. So having done that, we are also requesting this to be Dask, right? And we're asking for Dask chunks to be large, although they're larger than they are currently, we just have one single chunk for this case, but we'll come back to that. It's all right. So we have this data. It's haven't loaded anything yet, of course. This is all Dask. So we can, for interactive workflows, I prefer to usually do persist, right? So that the computation is done on the cluster. Is that the right cluster? Yeah, okay, it happened. And the other thing we can do is generate RGB images from that data. Clamp 13000, that means just that treat the 3000 as the highest, as the brightest value. By the way, Sentinel data is in 16 under the hood. It's I think it's 12-bit. And so we can, again, compute these things using Dask. It's all very quick. And then we're gonna plot imagery, right? And see, this here is completely just your standard X-ray machinery for plotting. And so the only thing here that is geospatial specific is this bit, right? The bit that that generated the Dask array at the first place. Okay, so we have a look at the imagery. We know, okay, right, on this day, so many clouds. So let's have a look how well the classification layer understands the presence of clouds in the imagery. So this is I have basically colorized the SCL band. By the way, contains a bunch of values that says this we think this pixel is water, or we think this pixel is a cloud, or the cloud shadow. And I have turned that essentially an image of integers into an RGB image by essentially replacing those things with those RGB values over here. So X-ray plotting is great and all, but sometimes you're really better off looking at an image. Sometimes the aspect ratios are not quite right unless you ask for it, right? So we can also convert this data into a JPEG image that is easy enough to view. And you can, you can open image in a new tab, for example, over there, which is, I'll come back to in a second. Why is it
And
useful?
do you have a sense of how much data you needed to crunch to get this image, or how much, how much from the Sentinel was used to?
All right, so this image is fairly small because we're using 80 megapixels, right? So let's have a look at, well, it says here it's only 27.39 megabytes, yeah? But the underlying data, if is, well, how about we get this thing copied. We get this thing copied and call it YY, because I'm not imaginative with names. And instead of asking for 80 megapixels, we ask for 10, right? And the beauty of Dask is that we don't need to actually load data to know to know the size of the data, right? So you generated a Dask graph, you have a look at the size, and you go, oh yeah, that's fine, that's manageable.
That's very cool.
And that's only like a gigabyte worth of data there at the native resolution. But because we are asking for 80 meter resolution, our software is smart enough to figure out that to read from the overview, because these images are stored as COG, cloud optimized geotiffs. They essentially include low resolution imagery in there, and DataCube is smart enough to for those data sources that have those overviews to read from the overviews. And that's why that one is significantly quicker than if you were to do it at the native resolution.
Cool.
What else can we do? We're gonna do the same image show with an RGB, and we're gonna do the same open image in a new tab, for example. And then with this, you can sort of compare, right? It's like a poor man's toggle between the imagery, so which can be really handy, particularly once you display it in the native resolution of the 80 meter things. You might see that. The OpenDataCube also includes these extra attributes on the product that describe how to interpret the pixels of bands like the SCL, which is essentially an enumeration type. And it basically has a mapping of values. You know, 0 is a no data, 1 is saturated or defective pixel, thin cirrus, and stuff like that. So we can use that information to compute. Oops, I forgot. We should probably ignore thin cirrus as well. We can compute the sort of the pixels that we don't really want to include into computation because we know that they are cloud. I'll just persist because, and that gives you an idea of, oh yeah, okay, I'm gonna throw away following pixels because they are cloud. Let's verify that looks fine by saying essentially we're gonna take the original imagery that we had, but now we're gonna replace all the pixels that we want to exclude with no data values. So in the Earth observation, it's common to use a special value as a no data value to mean that absence of value, right? So because we're not using floating point numbers that have not a number present, but rather int16s or uint16s, I think, and believe in this case. And I think for Sentinel-2, it's 0 is the no data value. Yes, it is. And so those utilities we have developed understand that, yeah, you want the no data of 0, I'm going to replace stuff. Anyway, so we're going to compute this and we're going to plot the version of it. And here we are. So we replaced some of the clouds with this bright pink background, which is transparency. So we can then also have a look at that image too, as a JPEG. And open a new tab. And we can toggle. Let's see. Yeah, sorry, that one, this one. And as you can see, the cloud detection isn't always the best. And you can see there's quite a bit of leaking out of the cloud. And we address that in our processing, data pipeline processing, by essentially expanding that mask of bad pixels out, again, also as Dask operation. And in fact, if I go back to my presentation, maybe, that's how our that's how our sort of real pipeline looks like. It's fairly complicated. We get the bands across different projections. We fuse them together. All these different squares, there are different squares, appear as one single raster. We then change the projection into the space we want to use for the final output. We fuse them again. We then do the same computation for the SCL band, where we take the SCL band to figure out where the clouds are, join them together across the different images. And so if the cloud classification is a cloud in one of the scenes but not in the other, which can happen in Sentinel-2 because those images are processed one granule at a time, one of those squares at a time. So there could be some disagreement. And again, we're doing this with the mask, and then eventually we apply the mask to remove the pixels we don't want. And we repeat that for all the different bands, and then we repeat that across different time slices before processing.
And where do you have the biggest challenges for memory management?
So the biggest challenges for memory management, so because this was with
so that's for all points in time.
Yeah, so this is for all points in time. So you see, so this was geometric median, right? GMAD. It's not practical to implement it as a sort of parallel iterative approach, right? It's not really possible. So it's like median. You need all of, except you also need all the values at once, except you also need all the values at once across all bands, which makes it even bigger. And data is stored sort of raster by raster, but accessed temporal column by temporal column. So effectively, it's a large matrix transpose operation, which are kind of hard to pull off. And we experimented with a lot of different things. We experimented with just your normal Dask solution, where we just had STAC and transpose and then the rechunk. And that kind of worked, but it was really hard to get to not run out of memory, because it makes a very complicated graph, I suppose. Primarily the rechunking that is necessary. And the reason why we need the rechunking, why don't we just go and say, well, why don't we just load it all in, across all time slices? And why don't we construct the chunk sizes the way we want them processed? Well, then we won't get enough parallelism, is the problem,
right?
Essentially, because the parallelism is across time slices, and if we put one single chunk per time, then things don't not enough tasks then. So that's where the challenge is when processing temporal dimension that cannot be done incrementally like a sum or an average can be done.
For sure.
Yeah. So what else? Surprisingly, is this the end of the demo?
It looks like it. And that was fantastic. So I've got a couple of questions, unless there's anything else that you wanted to cover with respect to your.
Oh, not really. I think this is fine, and we can also save those things to COG as well, which I'm not showing here, but also as a Dask operation. So is a lot of tooling that we are developing that is leveraging Dask, and the challenge is to develop tooling that works with both Dask and non-Dask arrays on input, because from the user perspective, you really want to see it as the same.
For sure.
And that's what Xarray is doing quite well, I think.
So perhaps stop sharing your screen, and I'm interested in the tools that you're building. Do you open source most things, or are there things which you keep in-house, and how do those decisions get made?
Most things, all the things pretty much are open source. The GeoMedian library does have a private component because it's been developed by a collaborator of ours from ANU, and it will be open source. But the optimization parts are not open source yet. But it is available as a less performant version is open source. Let's put it that way.
Okay.
So all the tools that I work are open source at Geoscience Australia. Yeah, so we are pretty good like that, and the data is too. So
yeah, that's fantastic. When we first chatted, and something we put in the announcement here that I'm really interested in, we said maybe we'll talk about some things to watch out for when using public cloud to avoid bill shocks.
Yes.
So maybe, this is an eternal question, right? So any tips and tricks, I'm sure our viewers and community would be interested in.
So we had several slip-ups as we were testing and developing those things. So the first gotcha for us was cross-availability zone traffic, right? So the first Dask cluster we were using, we just launched across multiple zones in Sydney, and that can rack up network builds pretty quick. I'd say rule of thumb is 10 times network cost per dollar spent on compute is very much possible if there are misconfigurations.
Wow. Yeah.
So if not more. So that was problem one we have seen. So if you are launching Dask cluster, make sure that in the same availability zone if it is on Amazon. So all the workers are. Another thing we had problem with is to do not so much with Dask, but with accessing data from S3. We had a misconfiguration where the data went through the internet, and that ended up costing quite a bit.
Wow.
Too. So yeah, and it's surprising how much that infrastructure can handle before you realize that how much it will cost you. But we have noticed errors starting popping up, and we sort of went, oh, hold on, what's going on? Why is this? We didn't expect that to change, and we stopped the computation because of that. But yeah, still racked up quite a bit in bandwidth costs because we were running it at high scale. A lot of parallel nodes doing a lot of stuff, even for a short time, can be expensive.
Well, I appreciate that. That's some hard-earned knowledge and hard-paid knowledge as well, right?
Yeah, that's true. But it's when it's right, it's cheap and fast.
Yeah.
And so And I guess the most cost is in storage, isn't it? Right. So, Geoscience Australia maintains a lot of data in the cloud, and I think the primary cost is storage. And storage is forever.
Right. But it's getting cheaper as well, right?
Yeah, let's hope so.
So as a final question, we've provided some notebooks from Geoscience Australia and access to the data as well. Are there any other resources that would be useful for people to get started, or stuff they can check out online for beginners?
Yeah, so the bucket that describes this thing, you can start have a look at what's available in terms of data, and there's a bunch of other tutorials.
If you put the URL in the chat, then I can in the Zoom chat, then I can just post it to YouTube as well.
Okay. So that's the description of the open data we were using in the demo.
Great.
And some links in there as well to access it with other tools other than Open Data Cube. So what else is Pangea? Is probably a good one as well.
While you'll find out, Constantine had a question. Do you use any special infrastructure for data stories on Kubernetes? For example, Rook, Ceph?
No, we are basically S3. We spent quite a bit of time changing our software to be S3 native, to read and write from S3. We have tried EFS every now and for like scratch space for notebooks, and I find the performance is really unpredictable. You really need to, So S3 is what we do in terms of, it's like the cheapest and fastest option, but less convenient, obviously, compared to a POSIX file system. I'd love to see, a POSIX file system that is S3 backed and is fast and easy to work with and has no glitches, but I haven't experienced that yet.
All right. Well, if anyone has, let us know in the chat or get in touch. Kirill, that's time for us, but I'd just love to thank you so much once again for coming and showing us your work and joining for what was a wonderful conversation.
Thank you for the opportunity. It was a pleasure.
Yeah. Fantastic. Thanks everyone for joining. Definitely check out Coiled Cloud. If you enjoyed this stream, hit subscribe, and we'll